All right, welcome back to undergraduate summer, everyone. I'm super duper excited to have Dr. Scott Carter here. He's going to tell us about permutations with quipu. I love all things related to string, so I'm very excited to hear what you have to say. Scott, take it away.
Okay, excellent. I have to push some buttons here. And remember which order in which to push them. That one seems to be working. And there we go. Okay, so it looks like oh, sorry. Wanted to minimize that. Let's try again. There we go. No, I don't seem to be able to. All right. If I get in the way of myself, please let me know. This is joint work with Youngju Bae and Byori Kim. And the woman here is Byori Kim, and this is her former fellow graduate student, Sun Mi. And as a test of my cultural relevance, Sun Mi is not a character in Cloud Atlas. Okay, this is a picture of Youngju Bae who's checking his phone. So if you want to do that, this is a good time to do that. And this is another photo that I have of Byori and my wife Hung. And it seems to be right after lunch because Hung is holding a smoothie that I ordered. Okay, so the plan of the talk is to exemplify quipu. I'm going to define groups and I'm going to use some terminology from group theory, but it will be minimal, and I'll try to remember to tell you what those terms mean as we go along. And I'll give quipu representations of things that are called dihedral groups. That's a scary word. That just means symmetries of polygons. And then we'll work with the unit quaternions, plus or minus 1, plus or minus I, plus or minus j, plus or minus k. And then we'll work with a couple of new groups. One is called the dicyclic group and the binary tetrahedral group. And I'll define those as we go along. Okay, so many of us, and I imagine Professor Jeffries might also think that this represents a generic matrix. And I'm going to skip from my outline immediately and tell you why we would think that that's a generic matrix. So I'm just going to draw the 3x3 case. If we have a matrix C that's the product of A and B, then in order to compute the ijth entry of C, you might go along the ith row of A and the jth entry of B, and you multiply term by term and then add those things up. So the ijth entry of C is going to be AI1 B1J plus AI2 B2J. And you can either go ... or you can go AI3 B3J. And so one tends to write that as a summation. Now, groovy people in the 1960s decided that it was cool to drop the summation notation. And in order to make them feel better, they called this Einstein summation convention. And when you do that, you wind up summing over repeated indices where one index is a subscript and another index is a superscript. And so you think about them tying together like that. And then you can think of this as AILBLJ. And so within these string diagrams that represent matrices, you sum over all the internal indices. This is a common phenomenon within physical systems. Summing over all possible entries is doing a matrix product or possibly doing an integral. So this tells you how a matrix acts. And if you don't feel like naming the matrix, then you could just denote it by a dot or a square or something. However, I really want this particular dot to indicate this matrix, and this is what I mean by a modulo 2 quipu. So let's see what happens if we compute that matrix product. Let's see, first row, first column, 1, first row, second column, 0, first row, second row, first column, 0, second row, first column, 1. So this matrix squares to 0, and that's why it's modulo 2. And so the relationship between the quipu is going to be this element is subject to the relationship that two of them along the same arc represents a straight string. And I've grown so accustomed to this that I forgot to tell you that this is a Kronecker delta function, which is equal to 0 if I is not equal to j, and it's 1 if I is equal to j. So that's the same thing as the identity matrix. And here's a multiplication table for this operation where in this entry, I'm telling you that I've put rows above columns. And so straight string together with straight string is going to be straight string with together with a dot in either fashion is going to be dot, and 2 dots gives you a straight strings. And this is what mathematicians call Z mod 2, or it's just parity, odds or evens. Okay, so a group is a set upon which there's an associative unitary binary operation that has inverses. So if we have A and B in the set, then we have A times B in a set. So that means that the operation is closed. It's associative in the standard sense that you can multiply the first two elements and then multiply by the third element, and that's the same thing as multiplying the second and the third by the first. And there's a unique element that's called the identity, so that 1 times anything is anything times 1 times, sorry, I said that the wrong way. Anything times 1 is 1 times anything is anything. That's what we mean by unital. And for every element in the group, there's a unique element that we call A inverse, so that A times A inverse is 1. And the nice thing about groups is that they could be lots of different things are groups. There are some notions that I forgot to define here. So if we have a subset H inside G that's non-empty, and it's also closed under product and inversion, then it's a subgroup. And if I have a finite group, I can write the group as a union of the subgroup. You take a group element G1 in the group, multiply it by H, then find something that's not in that set, take G2, multiply it by H, and so forth. And these other things here are called cosets. I don't think that those notions will bother us much in the future, but when you work with math for a long enough time, you start to use vocabulary that other people don't know of. So if you have trouble with the vocabulary, please let me know. Okay, so this thing is, I don't like this word, just Z mod 2, but if you also include crossings and you allow the crossings to, if you have 2 crossings, you can straighten them out. and you also allow the quipu to move up the crossings, then you get some new groups. I've written these as equalities, but indeed, I really want to think about the quipu moving up the strings as if they were bubbles in a fizzy drink. Okay, so let's play with this set of permutations with quipu.
Scott, just before we get there, I'm going to ask a kind of a dorky question.
Yeah, right.
Yeah. So by the way, everyone, feel free to interrupt our speaker from time to time. With these crossings, you don't care about under and over. It's like just an X, right? It's
That's
not
correct. Everything is a permutation. If you wanted to, you can think about them as physical strings, but you have to have a mechanism by which you can pass one string over another.
okay.
Yeah, but that's an excellent question. Yes, they're permutations rather than braids.
Okay, cool. Thank you.
Right, so let's play with this. And in order to do so, let's take this element that we had. And let's see what happens when we multiply it by itself. As I was practicing the talk, I kept hitting the Zoom button because I was saying, oh, this is going to be a Zoom talk. Okay, so when we multiply it by itself, what do we get? The crossing is the crossing is, this happens to me. Crossing is allowed to get rid of itself, so we can straighten those out. And then this quipu moves up. So we get a quipu over here, and we get a quipu over here. And let's see what happens if we put another one of those things in. And if we do so, we put that over here, right? And then we would get something like this. And which string has the quipu? The string on the left or the string on the right? I'll take that as a string on the right answer because of the time lag. And if we add, multiply one more time here, then we get back to the identity. And so we can say that this is x, this is x squared, this is x cubed, and this is going to be the identity element, and this is z mod 4. No matter what you do, you're just working at 3 o'clock would be the identity, 12 o'clock would be x, 9 o'clock would be the identity squared, or sorry, x squared, and 6 o'clock would be x to the third power. Okay, so some people like to call that clock arithmetic for that reason. Let's look at another possibility. So if we start with any one of these things, any one of these things, and square it, so we would get that that's the same as that. And if I put the one that has quipu on it, then all of these things will simplify down to identities. And for consistency, let's just make this all blue. Okay. So everything squared is the identity. And if we multiply any one of them by another, you'll get the same thing as if you did it in the opposite order. So those would both be equal to this. And I can do that in 3 different ways. And that, so this has the property that the group is commutative. And every non-identity element is squares to the identity. And so it turns out that this group is commonly known as Z2, whoops, cross Z2. It's also the direct sum, but I don't really want to introduce an other element. So you can just think about it as 0, 0, 0, 1, 1, 0, and 1, 1, where you add the things mod 2. If you take these things together and eliminate duplicates, so this is a duplicate and this is a duplicate, you can ask, well, what else can you create? So for example, if I, oh no, that's not going to work, so I have to do it like this. What happens if I take this thing and multiply it by this thing? Sorry, I'm calling them things because I don't have names for them. I don't know what they are yet. Oh, that's not such a smart thing to do. Let's do this instead. Let's take this one and multiply it by this one. Yes, okay. Then I'll get a quipu on the left. And if I take the one that has the quipu on the right and multiply it by, this, then I will get a quipu on the right. On the other hand, if I do things in the opposite order, so if I put this crossing with a quipu on the right with a crossing above it, then those things are not equal. So this is not commutative. And it does take a little bit of work, but you'll see that there are, let's see, 1, 2, 3, 4, 5, 6, 7, 8 elements. And if you just play with them, you'll find out that that's the only thing that there are. So this is a group of order 8. Let's see if this works. Of order 8 means it has 8 elements. And if you ask your phone, okay, Google, how many groups of order 8 are there?
According to Dana C. Ernst, it turns out that up to isomorphism, there are exactly 5 groups of order 8.
Okay, I liked that it actually gave a reference there, but I don't think Dana was the first person who discovered that.
Yeah.
So there are 5 groups of order 8. And one of them is Z mod 8. Another one is Z mod 4 cross Z mod 2. Another one is Z2 cross Z2. Another one is the quaternions, which we're going to talk about in a little while. And the last one is the dihedral group of order 8. I don't use standard notation for that. This is the dihedral group of order 8. So these are the elements, and I think that I labeled this element X. So let's see, X squared seems to be here. And X cubed seems to be here. And then I'll call this one R. And if I do this correctly, R times X is going to be this one. And Rx cubed will be this one. And then this will be R times X squared. So those are the elements. I seem to have left some space to play with these, but I think we've done enough. So it's beyond time to do some revealing on what's going on. So we think about this as this matrix, and this matrix would take the unit vector E1 to the unit vector E2. It would take the unit vector E2 to the unit vector E1. And so you can think about that as a switch of two things. This is called a transposition, and I might want to denote that as the transposition 1 switches with 2. Generally, you're supposed to separate these with commas, but I never will have a number larger than 5 or 6 here. So this does not mean 12. All right, now if I replicate the strings that are incoming, so a thick blue line is represented by thin black lines, then this diagram would correspond to this. This is very dangerous, okay? Everybody I know has a slightly different convention on how they represent permutations. And no matter what somebody else chooses, figure out what your representation is and work with it. Because everybody else's convention is going to confuse you. My convention is that the source of the permutation sits at the bottom of the string diagram, and this means that 1 goes to 3, 3 goes to 2, 2 goes to 4, and 4 goes back to 1. And that's what I mean by this cyclic notation here. Okay, so it's a little bit awkward for for looking at symmetries of the square, but let's figure this out. So let's see why the quipu can migrate. So within the permutation group, you have this relation. We might like to call that the Yang-Baxter relation, because it is. So it means that, for example, I'm going to speak in slang. 1, 2, 1 is equal to 2, 1, 2, or 3, 4, 3 is equal to 4, 3, 4. And those slangs mean these things that are like adjacent transpositions. So hopefully you've had a chance to see that here we have 1, 2, 1, that becomes 2, 1, 2. And then here I have 3, 4, 3, and that becomes 4, 3, 4. And so this migration of this quipu up this way is just a repeated application of that relation, which holds in the group of permutations. Similarly, 4, 3, 4 is 3, 4, 3. And then 2, 1, 2 is the same thing as 1, 2, 1. So that migration is the same, is a repeated application of this. Now, in general, that kind of application is going to occur. And as I said, this notation is awkward for a square. So I had to adjust the way I denoted the vertices of the square to fit with my quipu representation. So I'm going to think about the x-axis as being 1, the y-axis as being 3, and then this quipu represents a quarter of a rotation. And so here are the compilation of all these quipu representations. So this would be a quarter of a rotation. This would be a half of a rotation. This would be 3/4 of a rotation, and that would be a full rotation. So those are the powers of x. And then anything that has, or these 4 things rather, are going to be reflections. So the reflection in x switches 3 and 4. So the reflection in x is a reflection along the horizontal axis, the reflection together with x squared switches both. Was that a question? 1 and 3, 2 and 4. This one is a reflection about the vertical, and then this is a reflection about the southwest to northeast axis. This group is often denoted like this.
Oh, Scott, you've got a question from Michael.
Yeah, Michael, go ahead. I'm sorry.
Yeah, so I'm actually a bit lost starting from the previous page when you had a quipu inside a box.
Yeah.
How does it turn into? I didn't really understand how it turned into the diagram on the right side in the previous page.
Oh,
I think.
over here. Yes.
Yes, there's an X with a.
Okay,
with a dot
sure. Let's do that. Okay, so a pair of black strings is a synonym for a thick blue string. And so I have a tendency to try to flatten things out so that they're vertical initially. Okay, so this thick blue string is, so I should have probably used this picture here instead of this one here, so that we start out with 2 black strings there. So let's do that. We have 2 black strings. And another 2 black strings. And then the crossing here, I'm going to replace with these 2 black strings. Somehow I'm going to do this right. These 2 black strings. Crossing these 2 black strings. Like that. Okay. And then the quipu is up here. And so I'll replace that with this and that, and then go like that. And so, as I said, this diagram in the box is really the same thing as that. How's that? Does that help?
Yeah, that makes sense. Thank you.
Okay. So, and the string picture is a permutation. If you want to, you can rewrite the permutations as permutation matrices. So you can get them to act on Euclidean space, or you can just let them act on dots along the line. Okay. All right. So this was the group that we had. It's supposedly given by this presentation. It's generated by x. X to the 4th is equal to 1. It's generated by r. R squared is equal to 1. And the relationship between x and r is that. And I want to rewrite that relationship. And it turns out that rx cubed is also equal to xr. That's what I should have written, and I didn't. But those 2 relationships are the same. So here's the relationship that I wrote down. If I put rx down here or x cubed r here, then that will turn out to be, let's see, what is that? Both of those are these. They're quipu on the top of both strings. And so these should be equal. And the reason is that this quipu gets to migrate up here. And this one migrates there. Okay. More generally, we allow mod n quipu. And so for n equals 6, this is going to be something like this. The generator 1 is going to do It's always dangerous to do these things because visually it's very hard to count beyond 4, but this would correspond to my hexagon with a blue dot here and a 1 on the inside here. Okay. And if I stack one on top of the other, then I get, so there's this 1/6 of a rotation, then I would have 2, 6, 3, 6, 4, 6, 5, 6. And returning to Parker's question, since they are permutations rather than braids, that full twist gets to be annihilated. Okay, so if I look at the corresponding dihedral group, which is the group of symmetries of a hexagon, it's given by this. This thing has order 6. This will correspond to x, and r squared is also equal to 1, and then these relations hold. And what I'll do now, I warned you about this. This thing here is called a coset. Called a subgroup. Yeah, there's a question. Okay, this is a subgroup. So if I just look at the set of powers of x, we tend to write that as x with Langle-Wrangles around it. And so I just think about the powers of x as being x to the 0, x to the 1, x cubed, x3, x4, x5, x to the 6 is 1. And then if I multiply through by this element r into that subgroup, then you get these elements. Now, I'm telling you a lie that's convenient for me. Your group theory instructor will just tell you that the subgroup is an unordered set. And that's true. And the coset is also an unordered set. But I'm imposing an order on that of my choosing. In this case, the order is really a cyclic order, so it's living along a circle. And the coset would also have the induced cyclic order. And I'm doing that because it allows me to do what I need to do. Okay, so meanwhile, if I multiply x by capital X by little x, it just shifts everything this way. And I'll call that x with a shift of 1. If I multiply x times r times capital X, I guess this is where I used the wrong relationship. So I should have x r is the same thing as r x to the 5th instead of this relationship here. And both relationships hold. So that allows me to replace this here. Then I'll leave the r on the outside and then multiply through by the x to the 5th. But that shifts everything over 5 spaces. And then I'll put the r back in. And so x times rx is going to be rx to the 5th. R squared is the identity, so rx is x. And so I can represent the action of x by means of a picture like this. And then x squared, I just would stack this on top of each other. I think I'll do that like this. In shorthand, I'll put a 1 and a 5 here. I'll put a 1 and a 5 here. And then I'll add modulo 6. So 1 plus 1 is 2. 5 plus 5 is 10, which is 4 if you subtract out the 6. And if I keep doing that, I'll get 3, 3. 2, 4, 5, 1. And if you notice here, find all the ways of adding two numbers together to get 6. And so these are all the powers of x. On the other side of the coin, by the way, this is a birdie flying away. So that's what we mean by heads and tails. On some American coins, we have an eagle on the back of the coin. So I can't draw an eagle, but I can sort of draw a birdie. All right, so the powers of r are going to be, we put r here, and then r times x. This 5, 1 is because I put the r above the x. And so the quipu would move up to the other side. So they're the elements in the dihedral group of order 12, and they do these things like that. Rx is the same thing as x to the 5th r. If I take x cubed, I'll get 3, 3. If I take x squared, I'll get 2, 4. And I think this is everything else. R squared is the identity. This would be x squared. This one would be x cubed. X to the 4th, we get 4 over here, and 20 would give me 2, etc. So we just have to keep remembering what modulus we're doing, and you can think about these indices as sort of like odometer clickers. Okay, this is the most technical part of the talk, and it involves those vocabulary words. Namely, we pick an element in the group, and then we consider all the powers of x, and we order that as a subgroup. And then we write down all the cosets of that ordered subgroup, and then we think about the action of the group on those cosets. So one coset goes here, another goes here, another one goes here, one goes here. And so the cosets are permuted among each other. And then within the cosets, something happens. And that gives you that might be how a particular element in the group acts. And then if you just write that picture down for every element in the group, then you get a quipu representation of the group. For those in the know, this is a consequence of the Krasner-Kalygin theorem. And I'm sorry, my spelling in French is terrible, so I won't write that out. I should have written it out beforehand. Okay. Let me see how we're doing on time. Okay. The three-dimensional sphere is also a group. And the three-dimensional sphere is thought of as the set of all w, xi, yj, zk, where the sum of the squares of the element is 1. And I won't lie to you here. Anytime I need to do a computation with ij and k, I need this circle. And I also sometimes need this table. I can, off the top of my head, tell you that I times j is k, and that's the same thing as minus j times I. There are other relations that are encoded by this circle. So I times k would be minus j because we're going backwards along the circle. In a little while, I'm going to need an element that I'm going to call a. And I can compute a squared by means of the table that I had there.
Oh, Scott, we just lost your audio. Not sure if you can hear us, but your audio vanished somehow.
My audio vanished. How's that?
We can see the computer that you're,
Can you hear me?
the one your camera's going. Oh, try
Can you
again.
hear me?
Yay, we got you back.
Okay.
Yeah.
Sorry, Lisa tells me that collagene is not French. So
The spelling of the spelling, I can't identify it, but the spelling of this surname is not a French spelling.
okay. I apologize to Professor Collagene. Thank you very much for spelling it correctly for me.
All I did was Google it. Sorry.
But you have to know how to spell it in order to do that. Okay. Anyway, I'm interested in figuring out what this element a squared is. And so I'm going to use this table here. And in order to use the table, I'm going to mark out the things that are canceling. So everything there cancels, and then I'm going to go back in and add things up. So I get a -2, I get a -2i, I get 2j, and I get 2k. But everything here was divided by 2, and if you work out that means that a squared would be this quantity here. Okay, so I hope that I need that element. I'd like to talk about the three sphere, and I'd like to have a good picture of it in mind. I'm running a little bit low on time. I will tell you here that if you look at stereographic projection on the circle, the nice thing about that is that it gives you Pythagorean triples. And this is rather curious because Pythagorean triples have been known since the beginning of civilization. So I doubt that they did it by means of stereographic projection, but you never know. There are Babylonian tablets that have Pythagorean triples. If you do stereographic projection on the sphere, the point on the sphere ABC goes to this point in the plane. And in order to make that computation, I had to check it, so I just left my computation up there. I can't see the three sphere, but I can see the three sphere minus infinity. It looks like the room that I'm sitting in. And within the three sphere minus infinity, I have these other things. These correspond to the equators inside the three-dimensional sphere. And I was going to wow you with my sense of geography, but I think I'll skip that part. This IJK circle that we had before is actually sitting in the first octant of space by means of those circles there. Okay. I want to show you the four-string picture of the quaternions. And I see that I'm out of time, so I think I'll just finish with that. If I look at these cosets here and label them cleverly I, J, and K, then the action of the lowercase letters on those cosets is summarized here. And then these relationships, for example, I times I is -1 is reflected there. J times I is -k. J times I is -k is reflected in that quipu there. So that's that one. K times I is J. K times I is J is represented there. Let's just do this just a little bit more. I times J is K. So if I take I times J, I wind up at K. J times J is -1, so that would be there. And K times J is -I, that would be K times J is -I is there. And then there's the other relationship that you have there. So what's nice about these pictures is that they're actually summarizing a row of the multiplication table that I showed you before. So these are the elements in the quaternions. There's another viewpoint where we can think about the unit quaternions as living on this. It turns out it's a link of two circles in the three-dimensional sphere, and they can be presented like this. So this looks very much like the dihedral representation. So if I take I times J, I would get a representation for K. This is a really good place to finish, so let me finish that. As I said earlier, everything is secretly matrices, and I also did my whole o'clock bit with 3 o'clock, midnight, 9 o'clock, and 6 o'clock. And so I was trying to get you to think about the complex number I and think about them in that way. And so I can replace this diagram by a matrix where the entries are either plus or minus I. This diagram would give me this, and then K would be that. These matrices have determinant 1. If you look at the sum of the diagonal elements, their trace is 0. That's the sum of the diagonals, the trace of the matrix there. And I can use these quipu then to represent this thing that I call the three-dimensional sphere and write it as a 2x2 complex matrix that happens to be something called SU2. And there's certain things that are good to remember. Switch the diagonal, change the signs of the off diagonal divided by the determinant is one of those good things to remember. And so it turns out that any element in this group SU2 can be written in the form that we had before. Finally, if you take these 3 elements, divide them all by 2, and use the AB minus BA product, then you'll get back to your IJK from Cal 3 or Cal 2, whatever it is. And I could go on, but I've been asked to stop, so let's stop there. Yeah.
So this is the time of the seminar where we usually open things up for questions. One of the things I was curious is about, like, how did this all come about? What motivated, drawing these quipu, and like where did these diagrams come from?
So Professor Bay, Bjori Kim, and I were trying to understand certain quandals. And we were trying to understand the automorphism group of certain quandals. And we also had something called the Comology of Quandal. So we had our favorite quandal, which is the quandal that has 4 elements. And its automorphism group was A4. And we had an extension of the quandal, and its automorphism group we wrote down in terms of permutations. And then when we started to draw the permutations out as string diagrams, we noticed this quipu structure. And then we found out by doing an extensive Wikipedia search that the group of the extension was the extension of the group. So the group of the 8-element quandal that we got, the automorphism, inner automorphism group, was in fact the binary tetrahedral group. But we had this picture for the binary tetrahedral group, and it's also what is it? SL2Z over Z mod 3. And so then we started looking at tons of these groups like that. So that's where it came from. I'm going to skip ahead to a page. Well, yeah, maybe here. This is a good place to go. That binary tetrahedral group lives inside the 3-dimensional sphere. It gives you the 24 cell This is a very awkward picture of the 24 cell, but those are the elements. And then their quipu and the cosets form these hop links. Sorry, I'm gesturing with my finger rather than with the tool. The cosets form the hop links, and then where is there? Oh, there's another picture of it.
Whoa. Whoa.
Wait a second, but I need, I lost the page, right? So these are the quipu representations with mod 6 quipu. And I see there's a great time lag with me scrolling through the pages. Okay.
Are there other questions from the people on the chat or people in the room? Things people want to check out? Oh, there's a nice question in the chat.
Oh, sorry.
Does a crossing in a string diagram correspond to a semi-direct product at all?
Ah, very good question. Yes, these are secretly semi-direct products. The quipu are sitting as semi-direct products, and there is a let me see if I have that in here. I think I have it in here. No, perhaps I don't. I'm sorry. Yeah. Something that you should know about semi-direct products is that if you have a permutation matrix and you replace the ones in the permutation matrices with group elements, then you can represent certain semi-direct products that way. And I would imagine that somebody at U of T can show you how that works. Is there an expository article which exhibits the advantages of using string diagrams through concrete examples? Yeah. The article is only a manuscript, and we're turning this into a book. And if you search on the archive, it's a paper by Bae, Carter, and Kim, and it's on the archive. I don't remember the number of it. It's also will be superseded by a book that we're working on.
Scott, I can track down that archive link and put it with the slides if you want.
That'll be great.
The one last ask that I have as an organizer is for people to fill out this little feedback form about seminar. So this is feedback for Scott, but it's also the form that we use to sign up for getting treats, to get cookies and coffee and stuff. So it's very good form for admin reasons. But this was an awesome talk. This is our last talk before reading week. Our school goes on break for the next week. We're going to pick it next Wednesday, so not Wednesday of the week after. Thank you very much, Scott. It was awesome. It's going to round of applause. Yay! Awesome.
Thank you.
Talk to you soon. Thank you.
Okay.